Hello, good morning. Hopefully you can hear me. It's been a while since we last did a lecture. It almost feels new, but you're welcome. This is our second last lecture. After this lecture, I just have one or two things to talk about. So it may not be a full lecture after this one, but yeah, we will probably meet again. Today we want to do programmable logic device architectures, and we are going to finish this. This is nothing new. It's really quite similar to what we've already covered. But before we start the lecture, I just have a couple of announcements, maybe just one announcement. I've just been informed actually, so that I didn't upload lecture 14. I believe that probably I forgot. If there's a lecture that is missing and I want Maureen or one of the class representatives to ascertain that there's a lecture missing that I didn't upload, please let me know and I'll check my where I record these things so that I can upload it for you. Obviously, I'm going to upload this one. Now, the announcement I wanted to make was about the cut. So I'm going to give a test because I asked you people if you wanted the test or not, and you couldn't reach a consensus. Because I have, I should give two cuts, I'm happy not to if everyone agrees that they don't need it. But once 1 or 2 or 5, 20 people want it, then I have to give it, and then everyone has to do it. The other question is when, obviously, once again, you have failed to agree. And next week is there are exams for 4th years, so we have to do ours on Saturday this week. Actually, I'm going to see the custodians to make sure that we have access to the rooms, but I'm going to confirm that through Maureen, and please be prepared to do a cut on Saturday this week. It will be a simple cut in line with my style. It will be on 2 chapters: memory devices, and the interfacing with the analog world. So I will not set a number from this lecture that I'm going to teach today, but I will cover, of course, ADCs and DACs were part of the first cut, but I didn't really set a strong number from there. So I want to set a number from there for you, and then also memory. And remember, these things are really preparing you for the cut, for the final exam. So it is important that you focus. The other second announcement I want to make is a message. Yeah, I don't know. Some of you, okay, maybe this is not for the whole class, but some of you have missed some tests. Some of you have missed some assignments. If you are in that category, I really don't want to set new things for you. So in your case, if you don't want a retake, it's important that you read hard and pass the exam very highly. Now, let's start our lecture. So now you know that we've been dealing with, we've been creating circuits, logic circuits, and we usually create circuits to do, so for instance, you could say that you have your circuit here, the output does something. You might have a number of inputs. You can also have a number of outputs. In here is where we have our logic. So if this equipment is like a lift, it works in a certain way. If it is a microwave, it works in a certain way. If it's a security system, it works in a certain way. In here, you have certain functionalities or certain circuits that implement certain logic functionalities. Let me see, some people are sending me. Some of you are sending me uh, private messages, so please don't send me private messages because I think this affects everyone. They are saying that some of you are Seventh-day Adventists and cannot do this test on Saturday. I don't know what the policy for Makerere says about religious. Do Muslims not study on Friday? Hmm? I think we used to do tests exams on Sunday. I mean, I'm just here to tell everyone that if you wish not to do this test, it's okay. Don't do it. But that won't be my fault. Don't put that on me. But I'm not forcing anybody to do it. Anyway, I'll just continue with my lecture. I'm just going to be fair and try to check what the policy is on religious issues related to how we teach. But I want to give the test. Maybe you want to do it on Friday. Okay, fine. If you want to do it on Friday, it's fine. I'm going to communicate through Maureen this by the end of today. But for sure, we are going to do that test this week, whatever happens. Okay. But then, is if we do it on Friday, then now we affect the Muslims. You see, it's funny, guys, make up your minds. But feel free not to come for the test. I cannot force you to do the test. I'll just give you a 0, as simple as that. Yeah, so for now, let's go with Saturday. But I'll also check with custodians to find out the modalities of doing it on a Friday. Anyway, let's continue with the lecture. I'll look through your messages later. So now we can create, so let me say I've created a circuit and my output is, maybe output is CB A plus AB plus C inverse. Okay, something like that. I can create a circuit called a programmable logic device. Programmable, of course, we know programmable comes from memory, for instance. So programmable means that I can program. This can look like a PROM, something you program once. And in fact, as we go on through this lecture, you realize that indeed we do programming. We program by blowing fuses. Once you blow a fuse, you can't really put it back and blow it again. So that is right. You program it once, okay? Program it once, and that makes it like a PROM, a programmable read-only memory, or in this case, a programmable, one-time programmable logic device. And that logic device will always implement, this, so that as long as I have my CBA, every time I have this combination, I am going to get my output either high or low. It will always be low until all these conditions are satisfied, of course. Now, this shows you that we have sum of products, okay? So in our circuit, we are going to have AND gates and also OR gates. And we are about to look at an example. You can see that. Okay. We are not doing it on Sunday. Those who are saying Sunday, no. Okay. So we have this digital systems family tree, and out of the 3 main branches, we have standard logic. I don't know why my pen is not responding well this time. Let me see if I. Okay. Yeah, so we have standard logic, And standard logic includes our normal things, the gates, the flip-flops, and the MSI logic circuits. So these are the decoders, encoders, and no. So we know that we can create logic circuits using those. That's what we've actually been doing for most of our lectures in this year and also in first year, using these different devices, including gates and flip-flops and decoders and so on, to create circuits that perform certain functionalities. That is called standard logic. And under standard logic, you have TTL, transistor logic. You have CMOS technology, and you have ECL, which is emitter coupled logic. And CMOS obviously is complementary metal oxide semiconductor. So these are different technologies that you can use to create MSI logic circuits, and some of these obviously include gates and other devices. We know how to do this, that's okay. Now under this, we also have microprocessors and DSP, digital signal processing technologies. Here we write instructions, and then our devices perform, read these instructions and execute them. So these are like computers. Then where our interest is actually under ASICs. ASICs here meaning application specific integrated circuits. So you create an integrated circuit that is application specific. If I want a circuit that controls the lift, I create an integrated circuit with all the logic that I need to do that. If I want to create a security system for SEDAT, I go and create an integrated circuit that is application specific. And in this case, it would be application specific to the security situation at SEDAT. If I want to create for courses might have more doors or less doors. It might have more levels or less levels. So you would need to design a new function, a new circuit, an integrated circuit for this. The advantage of this is that because I'm creating one IC, I can have just one IC. Whereas if I was using, for instance, standard logic, you might find one IC includes AND gates, another IC has XOR gates, another one has flip-flops, meaning that you need to combine a number of integrated circuits to make your functionalities work. And so if you have one integrated circuit as opposed to many, you can benefit from the advantages of miniaturization, like less power consumed, less board space, cheaper manufacturing, and of course cheaper to buy, etc, etc. Now, under ASICs, it's where we have PLDs, and we've said that we can create these programmable logic devices for specific scenarios. So a lift, a microwave, a shopping thing, a security situation, and so on and so forth. We also have gate arrays, standard cell, and full custom. But these, anyway, let's continue with PLDs. Under PLDs, we can have simple PLDs, we can have complex PLDs, and field programmable gate arrays. Field programmable gate arrays and complex PLDs are together, can also be referred to high capacity PLDs. They just have bigger capacity. They are bigger devices than simple PLDs. Under these, you can have, I've told you already that it's like programming. It's EPROM, EEPROM, Flash, and so on and so forth. There are a number of pages around this, around 2 or 3 pages. Please go there and try to read through, because sometimes I pick some objective type questions from that area. So please go and read about that. Now, now let us look at the fundamentals of PLD technology. What is a PLD circuit? If I have 2 inputs and A and B, then I should be able to generate the different combinations of it, because we have said that this is a sum of products. Okay, so I should have produce AB, A inverse B, AB inverse, and AB, both of them inverted. These are the 4 products that are possible when you have 2 inputs, and you can use these to create your sum of products. So at the outside, I can have maybe output 1, maybe output 2, and so many other outputs. And my output 1 could, for instance, be AB plus AB inverse, okay? A inverse B plus AB inverse, which as we know is an XNOR gate. But why am I able to get this? It's because I have first of all generated the 4, and I pick 2 of them and combine them to get my output, or 1. Or 2 may be AB inverse plus AB. Once again, obviously, I could have another output 3, which is just A. I can also do that. And A is actually a product. It's A, but it's like B is 1, so it's still a product. I could really just come up with any equation at the output that I want. And so what we need here is to understand how the inside works, and this is what we are here to do. Let me duplicate this slide. Okay. So as I've just explained, our first task is to generate the 4 different sums of products. Each input, we have 2 inputs here, A and B. Each input is passed through an inverting and a non-inverting buffer. If I pass it through a non-inverting buffer, it will just not be inverted. It will stay that way. And if I pass it through an inverting buffer, it will be inverted. These are your buffers. This is the buffer basically. It is drawn like this because of the standard of representation or symbology, but this is the buffer. So you can see that we have our 2 inputs, A and B. These are what you access, but inside we create 4 lines. One is A, the other one is A inverse, one is B, and the other one is B inverse. Now these lines are called input lines because obviously they are from the input. It's just that we've created 2 lines from each input, one inverted, one non-inverted. We pass them through what we call an AND array. You know an array, so it's an array of AND gates. Just give me one moment. Okay, so I'm back. Sorry about that. Somebody was disturbing me here. So then we now create an AND array through which we can generate our 4 distinct products. These products are unique. So you can see that we have A inverse, B inverse, and the inputs are from the A inverse line and the B inverse line. This is A inverse B. The inputs are from the A inverse line and the B line because B is the non-inverted version until we create a B. So these are our 4 unique inputs, products out of the inputs, which is AB, AB inverse, A inverse B, and A inverse B inverse. Now, once we have, and of course, when you see a dot, like here, a dot is hardwire, okay? Hardwired, that's what it's like soldered. So that one is a permanent connection. Now, if you look at a place like this one, there is no connection there. It's just a wire going through. But if you want to make a connection, please put a dot. And this is important. If you don't put a dot, we don't know what you mean. Okay, so this is really key, and you need to remember that. Now, these are our product lines. We had input lines, which are the lines from the input. And now we have products lines, which are the products, which are the lines from the AND gates. Obviously, each AND gate gives you a product. So these are our product lines, and they contain unique products of the inputs or the inputs. So if we had 4 inputs here, we would need 16 lines, essentially. Now, we have what we call an OR gate array, okay? OR gate array. This OR gate array has inputs. Or in other words, they input each AND product. Each AND product finds its way to the input of each OR gate. Now the OR gate could be 4, they could be 2, they could be 20, it doesn't matter. It could be 1. Okay, so if your circuit here, remember when we were here, if your circuit here has 2 inputs, then you have 2 OR gates. If it has 5 inputs, then you're going to have 5 OR gates, and so on and so forth. So you can see that each OR gate is the same. It gets an input from each product line. That means, for instance, that O1 is equal to AB plus A inverse B plus AB inverse plus or I should say or A inverse B inverse. That's what it means. However, you can see that each line going into the input goes through a fuse. It goes through a fusible link. So those are the fuses that we use to program. If you blow a fuse, it means that the value going into the OR gate is a 0. If I've blown a fuse, there is no input. If I keep the fuse intact, it means that that product can pass through the OR gate. It can be ORed with all the other inputs that are going in there. So let us, for instance, look at OR1. I've actually created a bigger thing. Now let's imagine that here we broke off that one. Let me just go back and use black. Let's say that we have blown that fuse and that fuse. If we do that, it means that O1 is equal to, of course, A inverse B inverse, the fuse has been blown, so it can't reach the OR gate. So that's really a 0 if you like. These two in the middle can reach, which is A inverse B plus AB inverse, plus the fourth fuse has also been blown, meaning that that product AB cannot reach. So that's also a 0. And this is how, this is actually XOR. Now, I've created, at my output O1, the performance is an XOR performance, okay? Just like that. If I wanted to program, maybe I want to create, let's look at gate 4. Gate 4, I'm going to break that one. If I break the third one, then I will have AB inverse. The third one should be A inverse B, so that one is gone, can't reach the input. Then I'm going to have AB inverse, and then obviously AB. So here you could choose to simplify the equation to make it smaller, that's okay. And in fact, if you try, say, then you can see that you would have B inverse and AB. Okay, so this one, A will go. And we know that this can actually, I think, be B inverse or A. Okay, so actually this O4 is going to implement that. It's really as simple as that. So that is the way we program. You just come and blow certain fuses to get what you want. Now, if you look here, you can see that we have 4 product lines. So we have an OR gate that has 4 inputs, and each input obviously goes through a fuse or a fusible link. If we had 3 inputs, we are looking at an OR gate having 8 inputs and 8 fuses, of course. If we have 4 inputs, that goes to 16. If we have 5 inputs, that goes to 32. In other words, the inputs to the number of product lines are going to double every time we add an input, okay, to our circuit. And also the number of fusible links are going to double. That means that you're creating a lot of, this can be a problem, because if you have 10 inputs, you're looking at 1,000 plus fusible links, and that's quite much. Anyhow, you can also see that by drawing this, the clutter is too much. If I had an OR gate with 16 fusible links, you'd be seeing so many fuses. Industry came up with an idea of a standard way of symbolically representing this So to reduce on the clutter. So instead of having 4 lines, for instance, instead of having 4 lines, they are going to have 1. Let's actually go straight there. This symbology starts from the buffer. Remember the buffer was, you can see how the buffer was. It was this, and then add an inverter and do your 2 lines. You can see here that you just draw a buffer and you put a circle here. The non-inverting input line is that, and that is the inverting or the inverted input line. As simple as that. That reduces already on the clutter, and you can see that that's how we have done our things. If I want A inverse, I'm going to hardwire on the A inverse. If I want A, I'm going to hardwire on A. Okay, these are hardwired connection. And if there is no dot, there is no connection. So that's what I said earlier. If you draw your things, make sure where you need to have a connection, you put a dot and that it's clear. If it is not, then we don't know if that's a connection or not. Now you can see that you still have your AND array, but then you draw your product lines. These are our product lines. And instead of drawing 4 lines going into the OR gate, we draw just 1 line. 1 line going through all the 4. Now, 1 line going through all the 4 means that if we want to show that the connection is there, we put a cross. A cross tells us that that is an intact fuse, and where there is no cross, it means that the fuse is blown. So if we go back to this point, for instance here, I would be having my 1 line, okay? And obviously these are the product lines, A inverse, B inverse, A inverse B, AB, AB inverse, and AB. And I have my OR gate here, okay? So in this case, you can see that we blew fuse 1 and fuse 4. Now fuse 4 comes from AB. So if it's blown, I don't put anything. These ones, the middle ones which are not blown, I put a cross to show that the fuse is intact. And here, I don't put anything to show that the fuse was blown. If there is no cross, then the fuse was blown. So you can already tell from here that some programming has been done, because when this first comes, you would find crosses at every point, meaning that the fuses are there. But eventually, they will be blown. And when you blow specifically the ones you want, what you are doing is what we called programming. So now you come and blow this one, and that means that the inputs that are able to reach this OR gate are those 2, those product lines. So when E01 is A inverse B and A B inverse, which we said is the XOR. If you look at this one, the programming left only 1 product. That means that O2 is actually equal to AB. As simple as that. It's the only product reaching there. So it's just AB. But remember, when you have blown the fuse, the line will be hanging. And when we have looked at AND gates, we have said that the high is going in, but with OR gates, it's a 0. We take it as a 0. So it means that O2 would basically be 0 or 0 or 0 or AB, which is AB. Then you have this one. If you have that one, there's nothing, all of them are blown. So it's 0 or 0 or 0 or 0. And it means that our O3 will always be 0. No matter what the inputs are, it will always be 0, because those product lines are all blown. Here, all the fuses are intact. So that means you have AB inverse, AB, AB, and AB. That actually will give you a 1. Okay, if you do the math, if you do your linear, your Boolean algebra, it will give you a 1. So it means, of course, we say that when this PLD comes from the manufacturer, it comes with all the fuses intact, and you can blow them yourself, or you can ask the industry, obviously the manufacturer, to do this programming for you. It means that if it comes to you for you to program, all of the outputs will be reading a 1 until then you start programming to get what you actually want. So this is the symbology we use when I ask you to draw something. Use this symbology. Don't draw this cluttered one. You know, you can see so many lines, especially here. Don't draw that one. Please use this standard to draw your things and make sure they are clear. Right, let us look at some PLD architectures. Some PLD architectures, actually the one we've been looking at is what we call a PROM architecture, programmable read-only memory. The reason why they call it this is similar, is quite similar. You can see that at the input, we have also, like at this input for this diagram, you see on the right, we have DCBA, those are our inputs, and 16 possible combinations of those inputs, because we have to create products of these inputs. We must create products of the 4 inputs, and each product has got to be unique. So D inverse, C inverse, B inverse, A inverse, all the way down to DCBA, and every other product in between. Our inputs are DCBA. So you know that in a PROM or in memory, if you have 4 address inputs, they are going to resolve 16 memory locations. And if you consider that in the memory location, each memory cell stores a 1 or a 0, then you get an address, it goes into the memory, and you select one unique location for you to find whether it's a 0 or a 1. Now, in the same context, in a way, here we have our 4 inputs into a PLD, and each combination makes one line high or the others low. So that sounds like selection. And when you select, then it's like if your fuse is intact, it's similar to having stored the 1, okay? Because that high on the line will reach the 1. And if your fuse is blown, that is also similar to storing a 0 in that location. So here you look at this, and the way it performs, the arrangement and everything sounds like a ROM, but we call it a PROM like memory. We call it a PROM because it is one-time programmable. Once you blow a fuse, you cannot undo it, and so on and so forth. So you can see here that this is really just an expansion of what we have just looked at. You're going to have, just a moment. You're going to have in this product line, DCBA, and this is inverted, D inverse, C inverse, B inverse A, all the way to DCBA. Obviously, that would be DCB A inverse. And if you go back and see, you can see that D is the non-inverted, C is the non-inverted, B is the non-inverted, and A is the non-inverted. In this second one, D is non-inverted, C non-inverted, B non-inverted, but A is now inverted. Up here, you can see that all these 4 have been taken from the inverted line, and these ones, A is now no longer inverted, but these ones are still inverted. So and of course you do the same throughout. So you're trying to create all the 16 unique combinations because these are 4 inputs. Now PROM arrangements will work best where you need all the combinations, all the unique combinations available to you so that you can use them. So for instance, in a memory, you always need all of the different combinations of the address. Unless the address, the size of the memory is smaller than the address size, but usually that shouldn't be the case. Now we can use this in code converters, we can use them in lookup tables, because these you may need to use each unique input to find an output. Okay. The problem also with PROMs is that you have so many fuses. So for instance here, if we look at this OR gate, here, how many fuses are going in here? We said these are fuses, 1, 2, 3, all the way to 16. Each OR gate has 16 fuses going in. It means it has 16 inputs. And you have got to blow those fuses, and this can be a bit of a problem, a bit of wastage. Sometimes you don't need all these, but you can see that on the left we had wire, on the right we program. So if I wanted to program O0, because O0 as it is now, it is going to give me, because you can see all the fuses are intact, my O0 as it is now is going to be a 1. When everything is connected, your output is a 1. We have already seen that. Now, I may want to program this. I could say that O1 is high only when D, I'm trying to find something with fewer possibilities. Only when, I could say only when DCB is equal to 1. So when is DCB equal to 1? It is when both D and C and B are both 1. Okay? A can be 0 or 1, it doesn't matter, but as long as DCB is equal to 1, for you to have 1, it means both D or D of DC and B are 1. Otherwise, if one of them is a 0, then you're going to have a problem. Anyway, so the combination, I'm not going to teach this, I just made it up. But actually it is not like it's a lie. And so we can see that the only combination when D equals C is equal to B is a 1 is here. Okay, D is 1, C is 1, B is 1. D is 1, C is 1, B is 1. All the others, there is no other combination where D is 1, C is 1. Already you take out these ones because you can see D is 0. So take that out. D is 1 here, but where is C 1? Here D is 1 and C is 1. But now we also need B to be 1. Here B is 0. So these are the other two. So I end up with these last two lines. Those are the lines that give me D, C, B equal to 1. Now you can see that for the two lines, A can be 0 or in the other line can be 1. That's okay. But what I need in terms of programming is that I need to keep this fuse intact and that fuse intact, and all these fuses, I need to blow them. Then I'm going to have my output O0 equivalent to DC BA inverse, or, okay, because those are the only two, DCBA. And once you simplify that, you get DCBA. Yes, you get DC, because in the bracket you have A or A inverse, which is a 1. Okay, let us look at some more examples of how else could we program this? What if it was a bit more complicated? Let us look at O3. O3 is equal to AB or C inverse, D inverse. Now, you can see that here, okay, usually you can start with a truth table if you know how to do it. I'm going to teach you that method, but you could also do it from your head if you want, but sometimes I might say do a truth table, so you should do a truth table. Now, the way you do a truth table is that you're going to make a 1 wherever A and B are both high, and a 1 wherever you have C inverse, D inverse. So this C inverse, D inverse, C inverse, D inverse, C inverse, D inverse, C inverse, D inverse should all be 1. Then we go and look, there is no other way you have C inverse, D inverse as 0, 0. So we go and look for AB. When do you have AB as high? 1, 1. You have that one, okay? You have that one, you have this one, and you have that one. There is no other point where AB is 1. So really this is similar to, and okay, so fine. So in fact, if you sum up these combinations for the Doubting Thomases, if you do your Boolean algebra on these, you're going to end up with that. So I'm saying that if I give you an equation like this, in your truth table, you look for where this prevails and you make it a 1, and you look for where that prevails and you make it a 1. That is irrespective of the other inputs, whether they are zeros or ones doesn't matter. And I think you remember when we were doing kind of maps and creating those loops, we were, if I have AB, it means that in my loop, I have a combination of DC, okay, DC inverse, DC inverse, and DC, and of course AB, AB, AB. In other words, this is the one part of the loop that doesn't change. This one changes and so disappears. And so if you sum up these 4, you're going to end up with AB. For instance, this and that will give you D inverse AB, and this would give you D AB, and if you sum them again, that will go and you end up with AB. So this is how we create truth tables. I want to copy this and create a new slide. Right. Now, if I give you a question, you can do one truth table. If I give you a number of equations, you can do one truth table. You don't have to do different truth tables. So, what if I was doing, okay, let me put my, sorry about that. I'm going to put my O01. Let me put O1. O1 is A, B, C, D inverse, A, B, C inverse, D inverse. So I look for where C inverse and D inverse are zeros, and then I look for AB. So I will have a 1 here. This is O1. I'll have a 1 here. And then the other one is A inverse B inverse. I should look for A inverse B inverse. There are quite many. And then I look for C inverse D inverse, okay? No, CD. So I first look for CD. This is the point where you have CD. So I need to look for the combination with A inverse B inverse, which is 1, which I have. So I'll have a 1 here. The rest will be 0. If I'm doing O2, O2 is A, B inverse, C. So I'm going to look for a point where A, B inverse, and C, obviously D disappears because it is D and D inverse. So AB inverse. So it means I need to look for CD in here, and I look for AB inverse. A is 1, B inverse, B is 0. So this is my, in this case, I have a 1 here. Then I also now look for the case of D, AB inverse CD. I think I made a mistake actually. I made a mistake on this one. This is, okay, A, that's O2. AB inverse C is the same as AB inverse CD or AB inverse C D inverse. So if I take this one, CD is here, AB inverse AB inverse. Okay, so in the end I was okay. I have a 1, and then I look for AB inverse CD inverse, CD inverse. So we are looking at this, these 4, and I'm looking for AB inverse, which is this case, and that's a 1. All the others will be 0. Yeah, somebody is lost. Okay, now I don't think I'm going very fast necessarily, but maybe there's something. I'm trying we are trying to work backwards, and we did this with a kind of maps, I believe. I'm trying to go backwards from a simplified equation back to a truth table. If you can't get that, you should go back to your first year notes. It's there in Tochi. How do you go back from an equation, a simplified equation, back to a table? It's also the technique that we use with Kanoff maps. Let me explain or not, so that at least that one should be, you can get it. We have A or BD inverse or CD inverse. If I have A, it means that B, C, D have disappeared. How do they disappear? You know, with Kanoff map, if they are in the loop and they are changing, we know that those are going to disappear. Now, if I were here, I would say, if I'm at, my pen is giving me trouble. Okay, or not. Now, or not is every time A is 1, that is a 1. Because you can see, if I have my equation A or B, D or whatever, as long as A is 1, my output will be 1. It is the sum of products. So I'm going to have, every time A is 1, I'm going to have, I think probably, you know, there is a space there. So I'm going to have a 1 here, 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 a 1, and a 1. And then I can also find these ones. If you have B inverse, D inverse, no. As we have said already, if I have BD inverse, this essentially means that I have BD combined with BD inverse combined with the others are changing. So it is AC, the other combination is A inverse C, AC inverse, and A inverse C inverse. So they all change, and that's why they disappear. But BD does not change, it's common through them. Let me see some questions. Okay, I might have to redo this actually. Let me just repeat for those who may not remember. Maybe we will just do an example using a smaller equation. Let's look at the earlier equations. We had A, B, and we were looking at A inverse B or AB inverse, and so on. So let us create a truth table. I'm going to remove this. We are going to have 3 inputs, C, B, and A. Okay, so C, B, and A. This is 0, 0, 0, 0, 0. These are first year things, by the way. And I told you to go and revise those things, you refused. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right. Now we have our output. Let's say output 1. Now I'm saying output 1 is equal to something like AB inverse plus A inverse B. That is the XOR. So my question is, when do I have a 1 and when do I have a 0? I'm going to have a 1 every time I have AB inverse, and I'm going to have a 1 every time I have A inverse B. That is irrespective of what C is, because C can be a 0 or a 1. Let me first go to my table and find where A inverse B, no, AB inverse. This is A inverse B inverse. This is, okay. So A, B inverse. This is A, B inverse, okay? Because we can see a B is a 0 here. So I will have, let me use black. I'm going to have a 1 here. The other point where we have AB inverse is this one. I'll have another one here. Then I go to the other term. The other term is A inverse B. But even before we go to that term, let me first explain why I've chosen this one. This is actually similar to having it. The reason why C has disappeared is because it changes. So this is similar to A, B inverse C, or A, B, A inverse, C inverse. Of course, because this is common. So if I make a bracket inside, I'll have C or C inverse, which disappears. And if you look at this, you'll see that in one case, C is inverse, and in the other case, C is non-inverted. That's why it disappeared. Now, if we look at this other case of A inverse B, I'm going to look for every point where A is 0 and B is 1. I don't care what C is, as long as the combination is 0, 1. 0, 1 is here. The other 0, 1 is here. That means all the others will be 0. And so I can do my programming based on this. Let's do another example. What if my O2 was A? Okay, let's say AB C inverse. That's O2. If it is ABC inverse, I just look for ABC inverse. That's a 1. All the others would be 0. What if my output 3 was a B? Because it can be. For instance, in this case, you can see we have a scenario, all 4 inputs, but just 1. That's still a combination. But really what this means is that the others changed. It would mean that all 3 being equal to B, it means you had B combined with AC, A inverse C inverse, AC inverse, and A inverse C. Basically, it is O3 is equal to AB C or A inverse B C inverse or A B C inverse or A inverse BC. If you do this, you will realize that you'll end up with just B, and it is similar to the looping within the Karnaugh map. Anyway, let me remove this clutter so that we can continue. Okay, so here, if I have O3 and I don't want to deal with equation, I'll just go to the table and find every place where B is high and make it a 1. That's O3. So B is high where? There, and also here and here. The rest are 0. I hope that is clear to everyone, because we need to move on. So if we look at this, we can see that O3 is AB. So I first go to the table, I look for everywhere where AB is, and I make it a 1. AB is here, I make it a 1. AB is here, I make it a 1. AB is here, I make it a 1. And AB is here, I make it a 1. Then I go to C inverse, D inverse, which are these 4. I also make them 1s. And then I have my table. Let me repeat this for one more scenario. Okay. And just one more scenario for these ones. I'll start with A. Everywhere where A is a high, I make it a 1. 1, 1, 1, 1, 1, 1, and 1, 1. Then I come to BD. Everywhere where B and D are high, I make it a 1. Where is that? D is still 0 here, so that won't work. I'm looking at this range. B and D, this is 1 and 1, because you can see here, and also here, these 2, 1 and 1. Then I come and look for C, D inverse. This is C, D inverse. I find for C, D inverse is here, C is here. So I'm looking at this area here. I make everything here 1. And then the remaining is 0 really. I think these are the remaining zeros. So you should go and continue and try and do some practice. But let's go on and see how we actually now program. So O3, the first 4, we know that this is obviously 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, all the way to 1, 1, 1, 1. Now, when I want a 1, I leave the fuse intact. So that's why I have a cross here, a cross here, a cross here. These are the first four. Then I'll have a cross at these points as well. You can see you jump and put a cross at 7, put a cross at, I think that is 11, and put another cross at 15. And the rest are blown. You can see blown fuse. There is no fuse because these are zeros. So where these are zeros, you blow the fuse. Let's look at the case for let us look at the case for I think this is the simple one is actually O1 is equal to A, B, C inverse, D inverse, or A, B, wait. Well, that's also not very easy, is it? It has a lot of, anyway. So we look for the place where C inverse, D inverse are high. These are just two. So it is A, B, C inverse, D inverse, and A inverse, B inverse, C, D. Okay. So we have A inverse, B inverse, and CD. Those are the two places that we need to put a cross. All the others, we will blow them. And if you look at O1 here, there should be two fuses. One is at D inverse, C inverse, BA. The other one is at DC and B inverse, A inverse. As simple as that. All the others are blown and you're able, now your output O1 will always perform that way. It will always give you an output corresponding to the inputs DCBA. It will always be a high only if you have those two combinations. Otherwise, it will be a low. So we create these. We also have to write the equation of O1. If you program, you could write, but usually you have the equation from the beginning. You usually start with the equation anyway, and then you go and program. But I could tell you, I could give you a scenario and say, consider a circuit where the output is a high when a majority of inputs are high. So maybe it's a security situation and whatever. And so you can start with that. You get a truth table, you get an equation, and then after getting the equation, you can do your programming. I don't know which one precedes which one, but it depends on the question. Now, the problem with this is that it really requires, as we said earlier, it really requires scenarios where you need all the combinations. DCBA, all the possible combinations, which in this case would be 16. Sometimes you don't need all of those because you know, my equation is this. So why do I need all those combinations? So to move away from the PROM architecture, we can save space. We can make smaller circuits, easier to understand circuits, using another architecture called the programmable array logic. The other one is programmable logic array. Okay, and this is a programmable array logic, a PAR. Now the structure is the same. You have AND gates, you have OR gates, you have product lines, you have input lines, you have all that stuff that we talked about. However, in this case, we program the input and we hardwire the output. Before, you can see that now the X's, the fuses are on the input and the hardwired connections on the output side. Before, we had our hardwired in at the inputs, hardwired connections, and our programming at the output. Here, it means that we can end up with something linear. It is possible to create something linear and still be able to implement the same circuit. So let us look at an example here. You can see that when it comes, you still have your inputs with the buffer and non-buffer versions for all four. But instead of having hardwired connections here, we put fuses because we are going to come and program this and blow them. On the outside, we hardwire. So we can get the first 4 lines and put them into O3. the next 4 into O2, the next 4 into O1, and the next 4 into O0. Then we say, okay, what is my equation at O3? What really is going into O3? O3, it is basically, you can see that if all these are connected, what is this line? This line is DC BA. Actually, it is not DC BA, sorry. Before we program, this line will be D, D inverse, C, C inverse, B, B inverse A, and A inverse. And of course, that is equal to 0, because when you multiply or you add a variant, its inversion, then you get a 0. Hello. And all these will all be 0. All of them will be 0 until we program. Now, let us try to program. Let me say, for instance, that DC, that O3 is equal to DC B inverse A inverse. Just that. What does that mean? I have these 3 lines. I could say that here I need to program this to have DC B inverse A inverse, and then obviously, because you see these are hardwired into the output O3, for me to maintain that, it means I need a 0 here, a 0 here, and a 0 here. And we know how to get a 0 there. We get it by not blowing anything. If we don't blow anything, everything. Of course, you can blow some. Even if you blow everything and leave D and D inverse, you'll still end up with a 0. But since everything comes existing, why blow some if you are not programming? That's a question, really. So it's better to just leave them intact and you'll get your zeros. However, how do I get DC BA? It means I need to come and leave D and blow out D inverse, blow this one out. I leave C, I blow out C inverse. I blow out B because I need B inverse, I leave B inverse, and I blow out A and I stay with A inverse. So then the connection are really D, C, B inverse, and A inverse, and I'm able to get it here. And these ones are 0, so when all said and done, I will end up with that one. If we look at this output that was disturbing us, which was, for instance, it was output 0 being A or BD inverse, I think, or CD inverse. Yeah, BD inverse or CD inverse. How would I program this? I can come and say, okay, my output is here. My output O0 is there. So I need A here. I need B, D here, inverse. I need C, D inverse here. And here I need a 0. So where I need a 0, I leave everything intact. I don't need to program that. Now where I need A, where I need A, I will blow A inverse, leave A, blow these B and B inverse, C and C inverse, D and D inverse. I'll blow them, just have A. So A is the one that really reaches here and is hardwired into my OR gate 0. For BD, I will come and blow A and A inverse. I blow B inverse, I leave B. I blow C inverse and C, I leave D inverse, I blow D. And then for C, D inverse, once again, I blow D, I leave C, I leave D inverse, I leave C, I blow C inverse, then these ones I blow because they are not part of that equation. So that I have C and C inverse, and then that's a 0. And once I've done that, my output or not will be that. Yes, so you can see actually that, let us look at some example. You can see if you want AB, you come and leave A and B and you blow the others. So for you, when you are drawing your par, you don't put a cross. Obviously, for me, the crosses already exist. That's why I'm putting circles. But in this case, you can see D inverse, C inverse, B inverse, and A inverse are not connected because they are not part of the equation. Okay. For A, what if I just blow A inverse? So what if you just blow A? You can see A. When you want A, you leave A and blow the others, because you see, if you only blow A inverse, remember that's an AND gate, this would basically be D inverse. If you don't blow them, then they will get their way to the AND gate. C inverse, B inverse, and then you'll have A, because now A inverse is not there since you would have blown it, but these would still make a 0. Okay, so if you want A, you only leave A and you blow the others. Obviously here we want zeros, so we do not blow. What I was saying is that if you want a 0, you could blow everything and, for instance, leave D and D inverse. That would still give you a 0, but really, why go through the bother of blowing these when maybe it's just better to leave them unblown. So maybe if I have a 0, maybe in the future, if you want to change the program or the equation, it's now you still have some lines to program, and so on and so forth. Sometimes, so for instance, here we see that we have 4 outputs and 16 lines. So it's better, it's easy to say 4 lines per output per OR gate. And so that means that this equation, this par cannot implement an output that includes 5 terms, 5 or more terms. It can only implement 4 terms, since each line is a unique term, and we have 4 going in here. But for instance, if I had an equation with 5 terms, let's say that I had an equation O2, maybe, okay, whatever. O2 had term 1 plus term 2 or term 3 or term 4 or term 5. You have to think out of the box. So for instance, this one has 4 and that one has 4 as well. But this one only uses 3 of them. The others are 0. So maybe I could make this A, B inverse C, and I include this line into that so that I'm able to implement my 5 terms. Now, I could give you something with 3 inputs, C, B, A, and we know these are 8 lines, but I give you 3 outputs. If you give each of these 3 outputs 3 lines, you're going to end up with 9 lines, which you don't have. So it is okay to say that output 1 has 3 lines, output 2 has 3 lines, and output 3 has 2 lines. But obviously the equation have to allow. If you have 2 lines, it means you only have 2 terms or less. If you have 3 lines, you have 3 terms or less. If you have more than 3 terms, you're in trouble. It depends. So I could give you, for instance, output 1 with 4 terms, output 2 with 2 terms, and output 3 with 1 term. If that's the case, put 4 lines on output 1, 2 lines on output 2, and for output 3, you can put 1 line, and the other one you can also put 2 lines. One programs that, and the other one just gives you a 0. Okay, so let's look at an example. I have a par and I wanted to implement a 3-input logic circuit that returns a high output only when 2 inputs are high, and it also returns a high output when 2 inputs are low. So this is a 3-input logic circuit, CBA, that are called this output 1 and output 0, 2. Output 1 and output 2. It's okay to draw the same truth table. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now this first one, it returns high only when 2 inputs are high. 2 inputs are high here. Two inputs are high. Oh, what happened? Here, two inputs are high, two inputs are high, two inputs are high, and here two inputs are high. And obviously then it means the others are 0. For this one, it is two inputs are low. Actually, I think I've made a mistake. Only two inputs are high. These are 3. So this is a 0. And here it's a 0 because 3 inputs are low. This is only 1, 1, 0, 0. Oh, here two inputs are low. So these are high, 0, 1, 0, 0, 0. Okay, hopefully that's correct. All right. So let us draw our par. I've run out of space here, but I'll try to. So we have our buffer, non-inverting buffer. Okay, and this is C. B. And that's A. Then we are going to have our 8 AND gates in 5, 6, 7, 8. But I don't like how I've done this. So I will do smaller ones. 6, 7, 8. And obviously, I will draw a line through that. Remember, when this comes, it is all the fuses are intact, okay? But for us, it's better we program, because you see blowing a fuse means removing the X. But for us, since we are drawing, we don't need to put the X if we won't need it in the end. And then we have our outputs. And our two output lines. This is output 1, output 2. And now we can divide. Since we have 4 and 2 outputs, we can allocate, and each of the highs are just 3 per output, we can allocate 4 to each. So I'll put these through output 1. These are hardwired, and I hardwire these ones to output 2. Good. Now I need to come and program. The first one, if I'm looking at output 1, the first one is 0, 1, 1, which is C inverse BA. C inverse BA, I need to leave C inverse intact, B intact, and A intact. The others are blown. The next one is C B inverse A. So I'll make C intact, B inverse intact, and A intact. The other one is CB A inverse, CB A inverse. So I come and keep C intact, B intact, and A inverse intact. The others are blown. Now that should be a 0. And a 0 means all the fuses are intact. If all the fuses are blown, when we blow everything, it means we have highs going into the AND gate. I say that if you have a blown fuse, you have a high. If you have an AND gate, you look at that as a high, and that would give you a 1 because each one would go in there. And if you get a 1 and you sum it in an OR gate with others, then you'll end up with a 1, which is a problem, obviously. Now for output O2, the first one is C inverse B inverse A, which is that C inverse B inverse. Please don't draw the diagrams like me. This is C inverse B, A inverse B a bit neater, that's what I mean. And so A inverse is that, C inverse is that, B is that, and the last two, and lastly, you have C B inverse A inverse, which is C B inverse A inverse, and then that's a zero. A zero means all these should be intact. Now I'm going to bring a question on this, either a PAR or a PROM. Okay, so everybody can pass that. Usually I give it about 8 marks, so it's quite ample. And that really brings us to the end of our lecture and the end of this chapter. There are some other things in there, but don't read them. Just focus on the design. We are going to, I'm going to give you feedback on the test when we are doing it. Those who can't do it, please feel free to stay back. Those who can do it, be happy to see you. I'll give feedback through Maureen, hopefully before lunchtime, to confirm a date and time. If it's Saturday, it's 10 a.m. It can't be Sunday, so I'm really going to be looking at, I'm really just going to be looking at Friday and Saturday. Now, but very likely Saturday. Now we have put some work on Mugume. I believe it's available today from midday to midnight. Try and do it. They are really simple things, objective type things. Yeah, Edwin, as long as the test does not clash with my test, that's okay. I'm sure you've ever done an exam, 2 exams on the same day. So what are tests? Tests are nothing. If they say majority high, Moses, you go and do it. Actually, I don't know. You just go and do it. I brought something like this in the test. I think though it was majority are low. But if majority are low, then even when they are, if majority are high, even when they are 3, that's majority. So that's a 1. Here we said only 2. So that's instructive. That's really English. Can we not do the test next week on Friday? No. I mean, but you guys, I told you to go and give me a date. You waited, and now I've had to make the decision. Obviously, we have people starting next week exams. So the thing you don't understand is that there are people who have retakes, and they are in 4th year because you guys are in 3rd year. And those people need to be doing exams. So I think if I'm to be fair, I would be fairer to them because they're already doing a retake anyway. So we need to give them a helping hand. But also, I think it's more of a valid argument that I'm already doing exams, so I shouldn't be doing tests. Anyhow, have a nice day. If you fail it, it's okay. But hopefully you won't. I know you won't. You just want to get 100%. There's no voting, Davis. I'm a dictator. If I give you a chance to choose and you fail, then I dictate. Have a nice day.